Hello everyone. Today I am going to deliver fourth lecture. The learning outcomes are circular motion feed rates, feed rate for outside arcs, feed rate for inside arcs, maximum threading feed rate, maximum feed rate considerations, feed hold and override, feed per tooth, chip load and cutting times. I will try to explain about topics in two different techniques. First of all, I will explain theoretical approach, then after explain a numerical method. In this session I will solve total 13 number of different problems. First problem, feed rate for outside arcs, second problem, feed rate for inside arcs, then after two different problems, imperial and metric unit system of maximum threading feed rate, one problem maximum feed rate considerations, four problem, two in imperial units or another two in metric units for feed per tooth, and four problem, two in imperial unit and another two in metric units of cutting time. So now let us start the first topic, circular motion feed rates. Setting feed rates for circular motion is generally the same as for linear feed rate. In fact, most programs do not change feed rate for linear and circular tool motion. If the part surface finish is important, the normal feed rate must be adjusted higher or lower with considerations of the cutter radius, the type of radius cutting, outside or inside arc, and the cutting condition. The larger the cutter radius, the more reason the cutting feed rate for programmed arc will need some correction. In case of the arc cutting, the equidistant tool path after applying cutter radius offset may be much larger or much smaller than the arc programmed to drawing dimension. In most programs, the feed rate for circular interpolation is determined the same way as feed rate for linear interpolation. The cutting feed rate for arcs is based on established machining conventions. They include the work setup, material machinability, tool diameter, and its rigidity, programmer's experience, and other factors. Many programmers do not consider the machined radius when selecting the cutting feed rate for the tool. Yet, if the machined surface finish quality is really important, always consider the size of every radius as specified in the part drawing. Perhaps the same feed rate for linear and circular motion programmed so far may have to be adjusted either upward or downward. In lathe programming, there is no reason to distinguish between linear and circular tool motion regardless of the radius size. The tool nose radius is usually a small, only averaging 0.0313 inches or 0.8 mm, and the equidistant tool path is close to the programmed tool path taken from a drawing. This is not the case for milling contour programming, where large tool radii are normal and common. The adjusted arc feed rate is not required in every program if the cutter center tool path is close to the part drawing contour. No adjustment is needed. On the other hand, when a large diameter cutter is used to contour a small outside radius, a problem that affects the surface finish may occur. In this case, the tool center path generated a much longer arc than one in the drawing. In similar situation, if a large cutter diameter is used for an inside arc, the equidistance path will be much shorter than the original arc length. The elementary rule of feed rate adjustment for arc is that the normally programmed linear feed rate is increased for outside arc and decreased for inside arc, as shown in figure number 1. So my figure number 1 is your feed rate adjustment for circular tool motion. An outside arc of a tool path is longer than the drawing arc. An inside arc of a tool path is shorter than the drawing arc. Two formulas provides the tools to find the adjusted arc feed rate mathematically equivalent to the linear feed rate. Both formulas are recommended for external or internal contouring only, not for rough machining of solid material. So feed rate for outside arc. So for outside arcs, the adjusted feed rate will be higher than the linear feed rate. Calculated for this formula, O will be equal to your FL multiple capital R plus a small r divided by capital R. So where your FO is your feed rate for outside arc, FL is your linear feed rate, and capital R is your outside radius of the part, and a small r is your cutter radius. So now again I have go to discuss here the one problem. So based on the linear feed rate of 14 inch per minute on outside 0.375 arc radius required an upward adjustment for a diameter 0.50 cutter. So according to the formula, my feed rate for outside arc, so 14 multiple of your 0.375 plus 0.25 divided by 0.375 will be equal to your 23.333333. The result is a major increase to F23.3 in program. Consider the same example with 0.75 cutter radius. So diameter is your 1.5. So now again my feed rate for outside arc will be equal to your 14 multiple 0.375 plus 0.75 divided by 0.375 will be equal to your 42.0. So the feed rate changed from 14 inch per minute to 42 inch per minute, a 3 times increase. Here use previous experience to determine whether the adjustment is justified or not. Feed rate for inside arcs. So for inside arcs, the adjusted feed rate will be lower than the linear feed rate calculated for this formula. Fi will be equal to your Fl multiple capital R minus a small r divided by capital R. So where Fi is your feed rate for inside arcs, Fl will be equal to your linear feed rate. Capital R is your inside radius of the part and a small r is your cutter radius. So now again I have go to explain and discuss here another problem. So based on a linear feed rate of 14 inch per minute, the feed rate for 0.8243 inch inside radius with diameter 1.25 cutter must be adjusted downward. So my feed rate for inside arc will be equal to your Fl multiple of capital R minus a small r divided by r. So input the value here, the 14 multiple 0.8243 minus 0.625 divided by 0.8243 will be equal to your 3.384932. The result is a feed rate of 3.38 inch per minute in the program. This will be the applied feed rate for the F address. Now the next topic is your maximum threading feed rate. The selection of cutting feed rate in general was discussed earlier. After studying the section on the maximum revolution per minute selection, a spindle speed already discussed in my first lecture, how to calculate a spindle speed. It should not be surprising that similar limitations apply to the determination of a maximum threading feed rate for a given spindle speed programmed as revolution per minute. Again, the limits of the CNC machine tool are very important, so be aware of them when writing the thread cutting program. Maximum programmable threading feed rate for a given spindle speed in revolution per minute can be calculated from the following formula. So Fr max will be equal to F2 max by S. So where Fr max is your maximum feed rate for a given spindle speed, Ft max is your maximum feed rate per time in x-axis, and S is your program spindle speed, so revolution per minute. So now so I am going to discuss either one problems. So if the maximum machine feed rate along x-axis is 250 inch per minute and the spindle speed S is selected as 2000 revolution per minute, then the maximum programmable feed rate will be 250 divided by 2000 equal to 0.125 inch per rev. So therefore the maximum thread lead that can be cut at 2000 revolution per minute is 0.125 inches, which allows 8 threads per inch or finer. So the next problem is you're changing the spindle speed, so feed rate remain the same, will allow programming coarser threads on the same CNC lathe. For example, if only 1500 revolution per minute is selected instead of the 2000, the maximum lead will increase to 0.1670 inches or 6 thread per inch. The next example is in a similar example, using metric units, the maximum machining feed rate for x-axis is 6350 mm per minute and the programmed spindle speed S is selected at 1600 rpm. In this case, the maximum programmable threading feed rate will be in millimeter per revolution. 6350 divided by 1600 will be equal to your 3.969 millimeter per revolution. That means the maximum lead that can be threaded at 16,000 revolution per minute must be less than 4 mm. The calculated values only indicate the actual capabilities of the control and the machine and do not guarantee a safe job setup or even suitable machining speed. The next topic is your maximum feed rate. The maximum programmable feed rate for the CNC machines is determined by the machine manufacturer, not the control manufacturer. So for example, the maximum feed rate on a particular machine may be only 393 inch per minute, although the CNC system can support a feed rate several times greater. This is applicable for all controls, but there are additional programming considerations for CNC lathes, where the feed rate per revolution is the main method of programming a cutting tool. The maximum feed rate considerations. The maximum cutting feed rate per revolution is always restricted by the programmed spindle speed, so revolution per minute, and the maximum rapid transverse rate of the CNC lathe, it is quite easy to program the feed rate per revolution to high without even realizing it. This problem is most common in single point threading. A CNC machine cannot deliver heavier feed rate than the maximum it was designed for. The result will not be accurate. Threading result could be unacceptable when unusually heavy feed rates and fast spindle speeds are used in the same program. It is advisable to check whether the final feed rate does not exceed the maximum feed rate allowed on given machine. It can be calculated the maximum feed rate per revolution according to the following formula. F maximum will be equal to your R max divided by revolution per minute. So where F maximum is equal to your maximum allowed feed rate per revolution. R maximum lower of the maximum feed rate selected from the X and the Z axis. Revolution per minute, a spindle speed in revolution per minute. The R maximum is either in inch per minute or millimeter per minute depending on the input unit selected. So now discuss here one another problem. If maximum cutting feed rate for a CNC machine is 400 inch per minute and the spindle speed is 2800 revolution per minute, so what is the maximum allowed feed rate per revolution? So my F max will be equal to your R max by R per minute. So 400 divided by 2800 will be equal to your 0.1429. The answer is your F 0.1429. This calculation generally applied to single point threading. So now another is my feed, hold and overrides. So while running a program, the programmed feed rate may be temporarily suspended or changed by using one of two available features of control system. One is called a feed hold switch. The other is a feed rate override switch. Both switches are standard and allow the CNC operator to manually control the programmed feed rate during program executions. They are locked on the operation panel. The next topic is your feed per tooth. When we talk about feed per tooth, we are talking about how far the cutter moves when each teeth removes material or how much material is removed by each teeth each time it rotates. So as I discussed in the table feed per tooth is often referred to as different things. It could also be chip per tooth, which often abbreviated to CPT, but you may see different abbreviation in different equations, but these letters and these equations are just a placeholder. It's just an empty box to put numbers. So what we call them is not important. It is the calculation and the equation that is important to feed. Feed per tooth may also be known as chip load as well, and that would be normally abbreviated to C out. But again, you may see this abbreviated to different things. So our equations feed per tooth would look like this. It is feed per tooth represented by Fz, and our table feed F is divided by our spindle speed times the number of teeth. And this is how we come to our feed per tooth or our chip load, and the imperial equation is exactly the same. What makes it imperial is the table feed that we give. It would be an imperial and not metric, and that is what makes this equation imperial or metric. So just a table feed, so the answer to that would give us whether it is imperial or metric. So refer back to the table feed to calculate our F. In this case, okay, let us punch some numbers in these equations and play around and do some math to see how this works. Okay. So normally our feed per tooth information would be on the back of the tool packet, and we would work out our table feed from that. But if we know what type of feed and we want to calculate our feed per tooth, this is how we would do it. So let us do our first one in metric say. So now problem is my with a feed rate of 200 millimeter per minute and a spindle speed of 500 revolution per minute, calculate the feed per tooth for a tooth with 2 teeth. So our feed per tooth is represented by Fz, and if we give it a table feed of 200 millimeter per minute, so we are the metric this time, and we just divided that by our spindle speed. So we give our spindle speed 500 revolution per minute value, and we are going to times up by the number of teeth on our cutter. So say we are using a slot with 2 teeth. Now we just do this simple equation and it gives us out feed per tooth in metric. Say 500 times 2 would be a thousands, and we would say 200 divided by thousands, and that would equal our feed per tooth. 200 divided by thousands is 0.2,
and would be millimeter. So each tooth would remove 0.2 of a millimeter each time the engage with the material. So it is same as our table feed calculation. We just transpose in the equations to make feed precede the subject. Okay, let us try one in imperial. The another problem is your a spindle speed of 500 revolution per minute and a tool with 3 teeth would give us a feed per tooth of what when using a feed rate of 3 inch per minute. Okay, so find our feed per tooth in imperial. It is exactly the same. So our feed per tooth would equal, I am going to give a feed rate of 3 inches per minute this time. So because it is in inches, our result would be imperial, or 3 inches as a table feed, and we going divide that by a spindle speed. Say let us give another value of say 500 again, and we would times up by the number of teeth in our tool. So if we using an end mill with 3 teeth, we would use 3 number of teeth. Okay, so now we just need to do this equation. So 500 times 3 is 1500, and that would our feed per tooth set 3 divides by 1500 would equal to 0.002 inch of material that is removed each time the teeth engage with the material. Okay, so another metric one. So how much materials would a tooth of a 3 fluid slot drill remove with a spindle speed of 800 revolution per minute and a table feed of 720 millimeter per minute? So we wish to find our feed per tooth represented by Fz, and this time we are going to give it a table feed of 720 millimeters per minute. Nice fast table feed there, and then we would divided that by our spindle speed. So let us give a spindle speed of 800 revolution per minute, and we would times up on a number of teeth. Again say let us say this time we have 3 teeth on our end mill. So 800 times 3, quick easy way to do this 2400, and then we would just take our top number 720 and divided it by the bottom number. So if we do this would gives us an answer of 0.3 millimeter per tooth. So we are removing 0.3 millimeter of material each time the teeth engage. So that is our feed per tooth in matrix, working out from a table feed of 720 millimeter per minute, and we are using the spindle speed of 800 with 3 teeth of our tool. So that is how we work out our feed per tooth or our chip load. Okay, let us do one more to make sure we have really got this cemented in our mind how this works. So let us do one last one in imperial. My problem is a table feed rate of 32 inches per minute and a spindle speed of 2000 revolution per minute would give us what feed per tooth if we had a tool of big 4 teeth. So again we are looking for our Fz, our feed per tooth, and that would equal our table feed. So our table feed for this, let us give it 32 inches per minute. So another big fast table feed there, and then we would give it a spindle speed on n. So our n value, let us give it a spindle speed of 2000 revolution per minute this time, and again we times that by the number of teeth on our milling cutter. So this time let us use a 4 tooth end mill. Okay, so now we just need to do this equation. So 2000 times 4 would be 8000, and then we take the top from the bottom, and we are divided in case of 32 divided by 8000 would give us a value of Fz, our feet per tooth, and that would equal 0.004 an inch, and that is an imperial because our starting value here was imperial in 32 inch per minute, and that is the amount of material that's removed per tooth as engages at the material. So that is how we calculate feet per tooth. Now normally we are given the feet per tooth informations on the tooling information. When we speak to our tooling suppliers, they would supply the recommended feed per tooth full at all edges sold us. But if we know our table feed that we wish to work out our feed per tooth, this is the equations we do it. We are basically transposing our table feed equations to make feed per tooth the subject. The another and the last topic is the cutting time. So quite often when we are writing program using either CAD/CAM or G code, we are asked by our boss how long will this job take to make. It is important to work out whether there is profit in making this job, and it allows our bosses to bid for a price when they are talking to the clients and customers about this product. So it is worked out cutting times. We would use this equation, and this is to work accounts per length of cuts. By the way, so it is worked out the entire job, but we would have to do this calculation multiple times for every cut, but quite often we are asked for this equation. So this is how it works. Now there is two different way we can do this. We can do it in metric or imperial, and the only difference is that number that we give it, that is what converts it between metric or imperial. So for example, if we gives it a cut length and a feed rate in metric, we will get the times of our metric part. If we give those in imperial, we will get the time of our imperial part. So let us go over some of these calculation and do a few equations to see how this works. Okay, so in this first example, let us have a look at a metric one. A feet of 200 millimeter per minute would take how long to cut a section of material that is 20 millimeter long. So we are going to be calculated our time represented by the letter T, and this is in minutes. So our cut length is the first part of our equation. So let us say we are cutting a 20 millimeter long cut and we are using a feed rate for 200 millimeters per minute. So it is a simple case of doing this divisions sum here. So 20 divided by 200 would give us an answer to 0.1. Now that is in minute. They will take us cut this length. So now if we wish to convert that into seconds, we would just times it by 60. So 0.1 times 60 would equal 6 seconds. So our first answer, that one, this equation kicks out, this will give us it in minutes, and then we would just times it by 60 to give us an answer in seconds. Okay, let us have a look at an imperial one. So my problem is here, if we are cutting a 1-inch section at a feed rate of 32 inch per minute, how long will it take to cut in minutes? So this imperial example, we are going to calculate our time again, and we are going to say our cutting length in 1 inch this time. So we would have 1 inch divided by our feed rate, and if we give it a feed rate of 32 inch per minute, we would divide it 1 by 32, and that would give us our answer. If we do the divisions, it would give us an answer of 0.03. Now that in minutes, if we times that by 60, give us it in seconds. So we would get an answer of 1.8 seconds. So really quick feed rates and a really quick time to cut, it would only take 1.8 seconds to machine 1 inch length at a feed rate of 32 inch per minute. So one another problem. So one in our metric example. So this time a table feed of 150 millimeter per minute would take how long to remove 50 millimeter of material in second. So let us take our cut length of 50 millimeter and we are going to give it a feed rate of 150, and this is in millimeter per minute. So we just have 50 divided by 150, and that will give us a result of 0.33 of a minute. So we would times that by 60 to convert that into seconds. 0.33 times by 60 would equal 19.8 seconds. So that is how long it would take us to cut 50 millimeters at a feed rate of 150 millimeter per minute. So let us take a look at one last example. How many seconds would it take to cut a 6 inches long pieces of material with a feed rate of 3 inch per minute? Final imperial example, we are looking for the time represented by T, and I will give you a cutting length this time of 6 inches, and say we are cutting a 6 inch long length, and we are using the feed rates of 3 inches per minute. So it is a nice easy equation. We can almost see what the answer is here without a calculator. So T would equal 2 minutes exactly. Now if we wanted that in seconds, again we would just times the answer by 60, and that will give us 120 seconds. So that is how we do cutting time equations and calculation. So that is how we convert our feed rate and cut length into time. So congratulations, you have made it to the end of this courses. So now you have a full understanding of how to calculate your spindle speed, feeds, and in fact your manual machines are safe for more training on G-code programming, CAD/CAM programming, or machines of maps. We will have a full range of course plus lot of articles and videos on YouTube. We have a full range of courses plus lot of the free videos uploaded in YouTube. Carry on your study in this area. So thanks you again. I shall see you the next course.